Okay, welcome back and to the very last technical talk of the meeting. And well, we've had a lot of talks across all the areas of quantum mechanics, but maybe it's not that well appreciated that quantum mechanics has also had a big influence in mathematics. And of course, mathematics has always been a big of importance in quantum mechanics. And so this interplay between physics and mathematics through the quantum mechanical in the quantum mechanical universe. We'll have Nikita give us some vignettes from that. And as you see, it has to do with quantum field theory, but also graphene. So Nikita is a professor at the Simon Center for Geometry and Physics at Stony Brook. So Nikita.
Thank you very much. Thank you very much for organizing such a beautiful meeting. Rajesh asked me to give a talk for a broader audience, and partially fill the shoes of Dan Fried, who couldn't come. So I realized that it is impossible, so I will just give two talks. And so this whole thing could be loosely called between Sir Michael B and Sir Michael A. So you will see why. So I want to ask a few maybe inconvenient questions. One of them is, what is Planck constant? And in how many dimensions are we? This is not going to be a string theory talk. So this is going to be a talk from the point of view of some quantum mechanical system, which is trying to become self-aware and to understand where does it quantumness come and what kind of space-time dimensionality does it represent. So we'll be playing on the playground, which connects quantum mechanics and quantum field theory, not in the way we usually taught, or we were taught when we were in school together, that quantum field theory is in the first approximation, it's a quantum mechanics with infinite number of degrees of freedom, but I think the relationship is much more intricate and subtle than that. So let's start with something which I was supposed to talk about, namely that in quantum mechanics we have observables which form an algebra for the reason which is not completely clear, which is associative but non-commutative, and that's the famous non-commutativity responsible for the uncertainty principle of Heisenberg. So there is some algebra with some structure. You can multiply the elements of this algebra. We call them operators by numbers. You can there is a conjugation operator and so on. And in conventional quantum mechanics, this algebra doesn't come by itself. It comes with its representation in some Hilbert space, the space of states of this quantum mechanical system. And all this is meant to kind of represent, or was maybe the other way around, it was kind of geometrized by Feynman, who suggested that this could be interpreted as representing the path integral, the integral over paths, taking values in some in configuration space, or better in the phase space of a classical mechanical system. And so the matrix elements of the products of observables, time-ordered product of observables, would be computed by suitably defined infinite dimensional integral of that kind. And the non-commutativity of the product in that picture is a kind of a consequence of the topology, that you need to order this classical observable, maybe regularized classical observables, order on the timeline, and you cannot really push them one through another without causing some kind of harm. And so a priori you expect the results of the path integral depend on the order in which the observables are inserted. But there is a class of quantum mechanical systems called quantum integrable systems, in which this non-commutative algebra contains a rather big commutative subalgebra. So the observables which belong to that subalgebra actually do commute. And in fact, you might not like it, but we always use these quantum integrable systems in order to kind of talk about the spaces of the states of our Hilbert space, because this is how we label the vectors in the Hilbert space. We usually label them as by saying that they are eigenvectors of some commuting family of operators. And so this commutative subalgebra might not be very physical, because the time evolution might not respect it, but it is used nonetheless. So our language, even though when we speak, we place words in order, so the language in some sense is non-commutative, but the way we think about it has some commutativity embedded into it. So there's something to discuss about it. So because of that, because of the path integral nature of quantum mechanics, mechanical amplitudes, the commutativity is actually very surprising. So the fact that you can find something commutative is very surprising, because you should not be able to move things past one another. So in the last, say now, 30 years, a kind of a new view on quantization and also integrability has been emerging, which says that the commutativity is surprising unless there is another dimension in the game. And so here I like to quote the famous painter, who is famous for drawing the black square, and lots of activity in the art community has been dedicated to explaining what this black square represents. But the pupils of Malevich placed very specific stone on his tomb, and so this, in fact, this square is actually the face of a cube. So the meaning of black square is to make you think that there are extra dimensions which you just don't see, because you're looking at the problem in one direction. So by jumping a little bit ahead, imagine that you are actually now in quantum field theory. So you work not over time, but over space-time. And this theory possesses a fermionic symmetry, something which squares to 0, such that there are local operators which fit into the what is called descent ladder. So namely, the operator itself is annihilated by the symmetry. Here I actually mean commutators or anti-commutators. But then the derivative with respect to space-time of this operator, so something which measures how it changes when you change the position in space and or time, is actually a commutator with this fermionic symmetry. And so you can continue this process, and the result is that if you only study the correlation functions of operators which are closed under this operation delta, so they commute with delta, then the operators which are at the bottom of this ladder, so the original operator OK, can be moved around in the path integral. And so in this picture, so if I have, let's say, 2 space-time dimensions, now my observations defined as correlation functions will not change if I move things around. And so it is thus natural that the integrable quantum mechanics, or even somewhat integrable quantum mechanics, which has some kind of commutative subalgebra, maybe not the maximal one, descends from a high-dimensional theory, from quantum field theory, with something which you might call the topological subsector. And this is not as exotic as you might think. So basically, every time in quantum mechanics you see that you have some commutativity, then you should be looking for the ways of recognizing that the word line of your system is actually kind of a cylinder, maybe even high-dimensional space-time, just looked from far away. In the past, this was, of course, the cartoon for justification of string theory, but we can use it for other purposes as well. So a rich class of such quantum field theories with such a structure are theories which possess a certain amount of supersymmetry. So the minimal one, this is not the minimal one, but it's a kind of a small amount of supersymmetry. These are theories with 4 supercharges, and technically they're called D equals 2, N equals 2,2 supersymmetry. And the quantum systems which can be interpreted this way actually fill up the textbooks on quantum integrable systems, and lots of these systems are very much appreciated in condensed matter community. So the first one is the Heisenberg spin chain. So SU2 spin 1/2 spin chain, which was introduced by Heisenberg almost 100 years ago and was studied by Hans Bethe, who was prominently featured in the previous talk, in the early 30s. So Bethe found a way to diagonalize the Hamiltonian, which I didn't even write. So the Heisenberg Hamiltonian describes the nearest neighbor interaction of spins. And Bethe found an ansatz, a kind of a generalization of a plane wave ansatz, which describes the eigenstates of the system. It involves solving certain algebraic equations which nobody can solve in any practical way, except that in a limit when you have a very large number of spins and you look at the kind of density of excitations. But the fact that, so these are kind of very unique equations which describe the spectrum of the system, allows you to be kind of certain that if in any place in the universe you find such equations, then it means that somehow you are dealing with the Heisenberg spin chain. Can you hear me? Yes, I think something happened. Okay. Yes? My hair. Okay. So, yeah, now there is some echo. Okay, I will be holding my head high. So the story was that the equations which Bethe found, like 60 years later, 60 plus years later, were found in completely different realm of mathematical and theoretical physics. They were found as equations describing the vacua, the lowest energy states of some gauge theories. So in this case, the gauge theory lived in 2 dimensions and had a certain amount of supersymmetry, but it was essentially it's a gauge theory from the textbooks on gauge theories. So technically it's called gauge linear Sigma model, which represents it's a slight upgrade of the Sigma model valued in the Grassmannian, which were studied by a lot of people when asymptotic freedom was discovered in 4-dimensional gauge theories. The analogs of asymptotically free theories in 2 dimensions are Sigma models valued in some positively curved manifolds, and Grassmannians form a prominent series of such manifolds. And now, once this example was found, it was understood that maybe, well, it was expected that it was probably just the beginning of some story. And so soon after, a more complete dictionary was established. So, for example, if you want to study a spin chain, so mathematically, Heisenberg spin chain is just the first example out of a vast series of generalizations in which you can replace the symmetry group SU2 by any Lie algebra. And so the simple Lie algebras are classified as by ADE classification. And so if you replace SU2 or SL2 by any ADE type algebra, you will get the gauge theory, which will represent this quantum system, will be based on the quiver, which is built on the Dynkin diagram of that algebra. So here I gave you the example for the D type. So D corresponds to SO to N Lie algebras. So the gauge group for the Bethe gauge dual of this spin chain will have a bunch of unitary gauge group factors which correspond to the nodes of this diagram, and the green arrows represent bifundamental and fundamental matter multiplets, and the circles represent the adjoint fields. Now, so the equations which describe the eigenstates of a bunch of Hamiltonians, of the whole set of commutative Hamiltonians of the spin chain, which generalize those found by Bethe, coincide with equations describing the supersymmetric vacua of the systems. Now, the spin chain of Heisenberg was actually a very special case of more general class of systems where the spins can be sort of displaced in different ways. So these displacements are called inhomogeneities, and they map on the nose to the so-called twisted masses, so some kind of mass parameters of the gauge theory. Now, since the spins were organized along the circle, you can impose twisted boundary conditions such that the spin, the first and the last spin actually interact up to some, with a certain global SU2 rotation attached to it. So these rotations, in general, they are called twists, and they map precisely to theta parameters of the gauge theory. And in addition to so twisting and making things inhomogeneous, you can also make things anisotropic. So the original spin chain treated x, y, and z directions in the isospace equivalently. This is why it's called XXX spin chain, so all three couplings are equal. You can generalize them to XXZ or XYZ, which is partially anisotropic or completely anisotropic. And they map to lifting the theory from 2 dimensions to 3 or 4 dimensions compactified on the circle or the torus. So it preserves the same amount of supersymmetry. That is, the translational invariance is in 2 dimensions, but the structure of the theory is slightly changing. So it's actually a powerful method because it allows you to also generate quantum systems which you may not even thought about, because as I said, you have 2 textbooks. You have a textbook on quantum system, quantum integrable systems, quantum spin chains, and you have a textbook on gauge theories, gauge linear sigma models. And now you can go on and compare, and quite often than not, you find some gaps, and then you try to fill those gaps. So you can, so the spins which I was talking about, so these were finite dimensional Hilbert, they have, so these were systems with finite dimensional Hilbert spaces, because after all, well, you have a few qubits. But there are quantum systems where the Hilbert spaces are, of course, infinite dimensional. So this could be a many-body system describing a system of particles moving somewhere, or the spin representations, the representations of the spin group or spin algebra could be infinite dimensional. And so it turns out that once you go from this familiar set of gauge theories to still familiar set of gauge theories, but maybe slightly more complicated. So, for example, from ADE type Dynkin diagram, you can go to affine ADE type Dynkin diagrams. So this is the simplest one. It has one node and one loop. And you write the equations describing the vacuum of the theory, and then you go to, so in my case, I go across the bridge to YITP, Young's Institute for Theoretical Physics, where Volodya Karepin is sitting, who is an expert on spin chains, and I'm showing him these Bethe equations, and he says, I've never seen them in my life. So this is something new. And then you spend more time, you talk to more people, and then finally you realize that the equations which you describe actually describe the eigenstates, the stationary states of a quantum hydrodynamics in 1 dimension, though. So this is the rather celebrated equation. It's called, so the way I wrote it, it's a classical equation, but it has a quantum version. It's called intermediate long wave equation, and it interpolates between famous equations describing the motion of quasi 1-dimensional water. So in one limit, it describes the KZV equation, which is famous equation describing the waves in shallow water. And another limit, it describes quantum Benjamin-On equation, which describes sort of the deep waters. And so this is the interpolating system, which, so that's why it's called intermediate long wave equation. Now, in order to get systems which are of interest in other part of physics community, like many-body systems, one can continue this, leafing through the textbooks on gauge theories and go to theories in 4, 5, and 6 dimensions. So 4 is where we live, 5 and 6, not that far. But we want the theories. We want theories which have macroscopically two-dimensional Poincare invariance. So either we compactify them on tori down to 2 dimensions, or there is another thing which one can do starting in 4 dimensions, and that's to do the omega deformation. So the omega deformation is it's a procedure which sort of subjects the system you are working with to the angular velocity, or maybe several angular velocities. So one way to create it is to take a theory, if space permits. Here I'm discussing the example of actually 5-dimensional theory. So suppose you live in 5 dimensions, and 3 out of 5 dimensions have this shape. It's a quotient of R3, the 3-dimensional Euclidean space, by the there is a typo here, by the action of a lattice, just Z, which shifts in 1 dimension, just x by translations in one copy of R, and simultaneously rotates R2, the remaining R2. And so you close it up, so you have a period, let's say L in one of these R's, and then you rotate by the amount epsilon times L in R2. So you get some. So it's a flat background, but it's not globally trivial. So the metric is flat, but the holonomy of this flat metric is non-trivial. So it's a tiny example of Berry connection. So this can be done even in the limit when L goes to 0. So in that case, you'll get something which will look 2-dimensional times the 2 dimensions which are left hanging. So you get 4-dimensional theory, but the parameter epsilon remains as a deformation of your theory. So it's a theory with the Poincare invariance broken down to a 2-dimensional Poincare invariance, because I have to choose the center of rotation. But other than that, it's a nice theory. And so if one takes, let's say, the most famous gauge theory of all time, which is the maximally supersymmetric Yang-Mills theory in 4 dimensions. I mean, okay, it's most famous in some community. Most celebrated, let's say. And softly break it down to, so this theory has 16 supercharges. It's called n equals 4. And we can break it down to n equals 2, which has 8 supercharges, by giving a mass to some fields, the adjoint hypermultiplet in technical language. One gets what is called n equals to 2 star theory. SUN is a gauge group. This theory exists for any gauge group, but let me take SUN. And then, so out of 4 dimensions of space-time which you are given, 2 you make this rotational deformation with the parameter epsilon. Then so this theory does correspond to a quantum integrable system, and the system is also celebrated, but in other circles, many-body system named after Calogero and Moser. It's the elliptic Calogero-Moser system. So actually, one of the limits of the system is, which is trigonometric, is called Sutherland model, which Sutherland should also be mentioned there, of course. Anyway, so the point is that, so it describes, it's a non-relativistic integrable system. It has n particles which move in 1 dimension. This 1 dimension is actually a circle. And the parameter epsilon, so this angular velocity which I had in my construction, multiplies the kinetic term, epsilon squared. And so it is a Planck constant of that system. And the mass of the adjoint hypermultiplet determines the strength of the pairwise interaction between those particles. So this is the system when everybody interacts with everybody, pairwise. And all the features of this Hamiltonian are encoded in the structure of gauge theory. So the conventional system, which is the closest to, let's say, condensed matter applications, maybe in the context of fractional quantum Hall effect, would be to set the theta angle of gauge theory to 0. So then the period, so this is the elliptic function. It has two periods. In my conventions, one of the periods is equal to 1, and another is tau. And so this tau should be purely imaginary for this potential to be real. But this Hamiltonian makes sense actually for any value of the parameter tau. It will cease to be Hermitian Hamiltonian, but you can still study it. So you can still diagonalize it. Another famous system which is called super QCD. It's a theory with the gauge group SUN and 2n fundamental hypermultiplets. So when asymptotic freedom was discovered, it was found that the pure Young-Mills theory with gauge group SUN is asymptotically free if you add to it some number of quarks in the fundamental representation. So this number is bounded above by something proportional to n. There is some fractional coefficient. In supersymmetric world, these fractions become whole, and so this 2n is the maximal number of quarks, supersymmetric quarks you can add to gauge theory without making it infrared free. So this is the kind of a conformal limit. So this theory will be it's asymptotically it's conformal in the UV, but we'll study it with masses to giving masses to quarks. And so what it describes the Heisenberg spin chain, but now so it's an isotropic XXX type spin chain with n, the n is nc, the number of colors being the number of spins as before organized on the circle. But now the values of those spins, so the spins at different sites could be different, and they are in general complex, and they're determined by the masses. And the inhomogeneities are also determined by the masses. So you have two n parameters, n spins and n inhomogeneities, and they correspond to two n masses of these quarks. So these infinite dimensional spin representations, these are representations in the spaces of functions. So this is, I remind you how you can represent the algebra of SL2 by differential operators acting in, let's say, so one SL2 acts in functions of one variable. So you have n spin sites. The wave function of the system will be again a function of n variables, like a many-body system. Just the interactions are slightly different. And then again, it's a twisted spin chain. So there is a twist parameter which is determined by the complexified gauge coupling. So lots of results about these systems, this correspondence, which so many people work on that. So I'm just advertising, people who are closest to me. This is not an exhaustive list, of course. So the short summary of this conversation was that quantum mechanical systems quite often can be found as a low-energy subsector of quantum field theory, and typically gauge theory with some amount of supersymmetry. And the parameters of quantum system, including the Planck constant, quite often have geometric origin in this higher dimensional ambient theory. So in other words, we might be living in 4 dimensions. Let's say we might be living in 6 dimensions, but the set of observables we have access to only allows us to see the 4 dimensions which we experience. And so these quantum mechanical systems, they might think they are quantum mechanics, so they live in one dimension, but it's actually the restricted set of observables of a high dimensional theory. And this is not just it's actually applied physics in the sense that the fact that these things are embedded in high dimensional theory allows us to do computations which were not possible, by direct, straightforward methods. So, because due to the fact that we have developed methods of exact evaluations of certain quantities in supersymmetric gauge theories, I would say over the last 40 years, those methods give us answers to these quantum mechanical systems for which people could not find answers, like formulas for wave functions, some details about the spectra, and very importantly, so this bunch of parameters which I indicated, like most of these parameters were complex. So there is some complex analyticity of the spectra of these models, and there is a Berry connection of course, which allows you to transport states in the space of parameters. Now, there is another application of this embedding of quantum mechanics in higher dimensional theory. One of these applications gives you another perspective on quantum mechanics altogether. So let me briefly explain what it is. So suppose we've embedded, we realized our quantum mechanical system as a subsector of a four-dimensional theory. Now let me take this four-dimensional theory to live on a product of a cylinder. So the cylinder would be a time line across a circle times R2, but I will now curve R2 to make it look like a cigar. So it's a kind of a geometry which is asymptotically a cylinder, but then it's cupped at some point. So now, so this in the previous setup, so this cigar was where the omega deformation was taking place. These were the macroscopic dimensions of the d equals 2 supersymmetric theory. I just made the space of that theory compact. Now I want to make another reduction from 4 to 2 dimensions. So previously, this omega deformation essentially localized interesting degrees of freedom at the tip of the cigar, and so you were left with the macroscopically two-dimensional theory living on the cylinder. Now I want to reduce along the circle, these two circles, which you see on the right of this picture. So you'll get a strip. So the strip is a product of the timeline and the semi-axis, which parameterizes the radial direction of the cigar. So in principle, so this should go off to infinity, or if I make cigar finite, then it will be a finite strip. So when you do the analysis of the reduction of gauge theory along this two torus of isometries, you'll find, after some dualities, that you get a two-dimensional sigma model on the complexified phase space of the classical system, which represents the classical limit of a quantum system we were talking about. So it's important that the phase space gets complexified. And because in this way, you get a very straightforward connection to maybe more traditional way of thinking about the path integral as, so if you think about path integral as exponential integral formally, you can try to decompose it as a sum of integrals of periods over the so-called Lefschetz symbols. So Lefschetz symbols are the half-dimensional cycles in the complexified space over which you're performing your original integral, which are which originate at the critical points of the analytically continued action, so the thing which is in exponential, and then follow the path of the steepest descent with respect to the real part of what you have in exponential. So these are the contours which facilitate the convergence of the integral. Now, these contours happen to be almost surely they sit in the complexification of the space where you wanted to perform your original integral. So if I follow Feynman prescription of doing path integral over the paths which take values in the phase space, in the real phase space of my quantum mechanical system, the Lefschetz symbols will tell me that I should be looking for the critical points of the action where the paths take values in the complexification of the phase space. And then I need to find the path of steepest descent with respect to the real part of this complexified action. So if you think about it, now you've gone from the one-dimensional problem where the path was parameterized by time to a two-dimensional problem where the second parameter is the parameter, it's a time along the gradient descent trajectory. And so this two-dimensional kind of world sheet, emergent two-dimensional world sheet, is precisely this two-dimensional world sheet which I showed in the previous transparency. And so that actually helps to understand where the quantum tunneling takes place. So if we declare the reality to be the stationary point of the action, which determines roughly the position of this Lefschetz symbol, then most surely this stationary point will be a trajectory, so the trajectory parameterized by the real time, but taking values in a complex phase space. So these are not, so if you think about a double well potential, this is my favorite example. So if you think about double well potential, and you have a classically allowed motion when you bump around near the classical vacuum, and what you read in textbooks, there is a tunneling which takes place under the potential hill. The actual critical point of the complexified action takes you completely in the complex domain, so you actually start winding around some torus in the complexified phase space, which is kind of a nonlinear superposition of the naive tunneling under the hill and classically allowed oscillations and tunneling back. So these are kind of nonlinear superpositions of instantons, anti-instantons, and classical and perturbative oscillations. And so you have two integers for each degree of freedom, which parameterizes these trajectories. So this, in that sense, quantum reality is complex. Now, quite often, the target spaces, these complexified phase spaces, are Hitchin moduli spaces, and so that gives a practical tool for doing computations in geometric and analytic Langlands program. Unfortunately, this is not what Professor Sarnak was talking about. So quantum reality is not yet adelic, which would be really cool if we manage to do that. I think it is related to the difficulties of finding the Hamiltonian, which Sir Michael was talking about, the Hamiltonian which will produce zeros of zetas for the spectrum. Okay, sorry for the typo. So the final piece of that story is the separation of symmetry and state. So remember, I started by saying that in quantum mechanics, we have the algebra of observables together with this representation of the Hilbert space. But mathematicians like to, and maybe philosophers, and maybe we all should separate entities. So symmetry is one thing, and how we represent it is another thing. And so this picture with two ends of the strip allows you to do that. So for example, just really quickly, as you can learn from Professor Mukunda, the spin 1/2 representation of SU2 can be viewed as a quantization of the compact sphere. And the representations of another real form of that group, SL2, are, let's say, principal series representations, continuous representations, are quantizations of something non-compact, like hyperboloids. And so straightforward path integrals on these phase spaces are quite different, but they're connected in one framework where we study the two-dimensional Sigma model on the complexification of the sphere. So this is the space of complex solutions to this equation, which contains both the compact sphere and the hyperboloid. And so this picture of, so this worldsheet actually turns out to be the worldsheet of a topological Sigma model. And it has different types of observables. So observables which can only be defined on the boundary. And so for them, one still one gets this associative but not commutative product. And then there are observables which can be moved in the bulk, and there they can be exchanged. So they form the commutative subalgebra. Okay, I'll skip these mind-blowing applications because they tell you that in the framework of quantum field theories, not theories coupled to gravity, you can actually move between quantum field theories by certain non-local operators, which are the weak rotated versions of domain walls. And so if not for gravity, we would not have had the problem of landscape. But unfortunately, or maybe fortunately, so this is modified by back reaction of gravity. And now on something completely different, I have 11 minutes. So this is about, so thanks to Spenta, who pointed me to these newsletters. So the work of, how the work of Narasimhan Seshadri and Atiyah Bot might be useful in condensed matter physics. I mean, I'm sure condensed matter physicists know without me, but this is just one example which might be of interest. how two-dimensional gauge fields and twisted bilayer graphene are talking to each other. So this is the work almost done with my student, Vasily Yugov. So let me remind you what is twisted. Maybe there were talks, maybe I forgot. So you take two graphene sheets, you place them one on top of each other. So there are actually two kind of stable configurations. One is slightly energetically more favorable than another. Then you twist one relative to another, as in this picture, and a moire structure emerges, some kind of a large period compared to the fundamental lattice spacing emerges depending on the twist angle. And so this is the system which has been analyzed for some time now. One interest, so for me, the interest in that system is that it's a non-relativistic system, yet it can sort of model the relativistic physics in some limit. Of course, the fact that graphene could be a good playground for studying in the lab relativistic physics was pointed out by at least Gordon Semyonov in the 80s. But this is an interesting new type of relativistic physics, which turns out, so because of the two-layered structure, so the electrons not only propagate along the graphene sheets, but they can also hop between the sheets. And so the effective Hamiltonian, which describes it, looks like, after some simplifications, looks like a Dirac operator, in fact, like a chiral Dirac operator in two dimensions, coupled to an SU2 gauge field, where there is some potential which has essentially double periodicity up to a phase. So if you multiply U by a phase and this guy by the conjugate phase, then this can be done by a gauge transformation. So this is as good as periodic. And as we'll see later, there's an additional symmetry having to do with the symmetry of hexagonal lattice of order 6. And so this non-abelian structure becomes quite important. So it was observed, I think numerically first, that for certain magic values of the twisting angle, this Hamiltonian has exactly flat bands, meaning that it has normalizable zero modes, which exist for any value of quasi-momenta. So you can impose quasi-periodic boundary conditions, Bloch waves, and the zero modes persist. So people propose that maybe these flat bands will be responsible for superconductivity because the electrons can interact strongly. And now it's finally nice to put a face to a name. So my goal, humble goal, would be to explain geometrically what is the geometry behind this appearance of these flat bands, what's going on there, and maybe produce a numerical algorithm for finding the zero modes. So recall that for the abelian, let's say U1 electromagnetism connection on a bundle over a two-dimensional torus, there is an index theorem which tells you that number of zero modes of Dirac operator minus number of zero modes of conjugate Dirac operator is given by the flux through the torus. And also for generic gauge fields, one of these spaces vanishes. So if you have a flux, then and maybe slightly perturb the gauge field without changing the flux, then you know the dimension of the space of zero modes or the conjugate ones. But in our case, so this torus which I'm talking about, it's essentially so you take the Brillouin zone and identify the sides. So you make it into a periodic. You make it a compact space. So that's a torus which is flat, and the gauge field which I wrote was a SU2 gauge field. So the trace identically vanishes. So the index vanishes, and so we cannot say anything about the presence of zero modes. If they appear together with conjugate zero modes, and it's not a stable situation. But what might be stable is that the zero modes appear in families of gauge fields. So some kind of a family index theory might be at play. The only person who could expertly teach us about it is Dan Fried, but he didn't come, so I'll do something else. So let me first remind you that, of course, the existence of zero modes is a feature of a larger symmetry. So they don't, the fact that you have a zero mode of Dirac operator doesn't change not only under conventional gauge transformations, under SC2 gauge transformations, but it also doesn't change under the complexified gauge transformations. So I can take this matrix which I had on my previous slide and perform the gauge transformation with SL2C valued matrix field. And now this is, again, so I remind you, this is happening on a two-dimensional torus, so it's a complex plane identified with identification by the shifts by two periods. So one of the periods, its just normalization can be taken to be 1, and another one is conventionally denoted by letter tau. And in our case, this tau is the 6th root of unity, so it's located here. So the fundamental domain for this torus is a union of two equilateral triangles. That's going to play a role in what follows. But let me first start with general tau, and let me remind you that in the context of three-dimensional Chern-Simons theory, on the product of sigma is my torus now, cross R, the states of Chern-Simons theory, which are also known as conformal blocks of the current algebra, are the functionals, so the analytic functionals of the gauge field AZ bar. You can think of them as being generating functions of the correlation functions of the currents in your conformal field theory. So I'm sorry for the typo. So they obey the Kosaikal condition that if you gauge transform AZ bar, so here should stand this guy, then you get psi itself times certain factor, and the stability, so there's a notion of stability of the orbit. So the orbit of AZ bar under the GC transformations is stable if there exists a psi which solves this equation such that it doesn't vanish on a given gauge field. Now for physicists, so psi, this is a conformal block of a current algebra, but you can think of it as a kind of a determinant of Dirac operator coupled to this background field AZ bar. And so being non-zero means that your operator doesn't have zero modes. If your Dirac operator has fermionic zero modes, then they will make the integral vanish. And so that's why it's tied up to stability in mathematical sense. Now, Narasimhan-Seshadri theorem says that, one of the formulations, that the bundle is stable, so this AZ bar is stable if there exists a complex gauge transformation for which the curvature of the resulting gauge field is 0. In other words, you can endow the holomorphic bundle with a Hermitian metric such that the associated unitary connection is flat. And so this is the intuition behind the stability using free fermions. Now, the way to achieve that is to do certain work. So this work is called Yang-Mills flow. And what it does, you take your gauge field, which you start with, and then you run the parabolic differential equation, which moves it according to the equations of motion of Yang-Mills theory. So we take the Yang-Mills functional. It's two-dimensional Yang-Mills functional. This is its derivative. And I make my gauge field change according to its derivative, maybe with some compensating conventional gauge transformation. And so the point is that we try to minimize this functional. The good thing about this equation is that it actually transforms AZ bar by complex gauge transformation. So what I'm doing, I'm performing complex gauge transformation on the field in a way which depends on this field in such a way that the value of the Yang-Mills functional decreases. Okay, I had to speed up. This is analogous. So let me give you a fine dimensional analogy for this procedure. So let me replace the space of all unitary connections, all basically all gauge fields, by fine-dimensional vector space, C to the n. And the group of gauge summations, unitary gauge summations, I will replace by the group U1, which simply acts by multiplying all these by the same phase. The analog of the curvature of the gauge field is the moment map for this U1 group action. It's the sum of absolute value Z squared minus some constant. And the analog of the level K, so this is like K, R is like K, conformal block is a homogeneous polynomial in Z1, Zn of degree K. And so the algebraic geometric stability for a choice of the point Z is such that it is stable if there exists a polynomial, homogeneous polynomial of positive degree, such that it doesn't vanish on this point. So I'll leave it as an exercise to figure out for you what are the points which are stable. And the differential geometric stability is that there is a complexified transformation, so basically rescaling of Z1, Zn, such that you can make this quantity F, this one, vanish. So it means that by rescaling, you can make your Z's to belong to a sphere of non-zero radius when R is positive. But let's not do it in a simple way, let's do it in a hard way. We'll run the gradient flow, the analog of the Young-Mills flow, and we can solve it. And so what it does rescale you to the point such that when time goes to infinity, if the original point was not zero, then you will reach the sphere when f equals to 0. If the original point was equal to 0, you will always stay at 0. You will never reach the sphere. So there is one unstable point in this example. It's the origin. Back to Young-Mills theory. So this study of flows and critical points of this flow has a rich theory. So that was undertaken by IT and Bott in the 80s. And so it is not hard to see actually where can you stop. So you run this flow, and typically with 100% probability, you will end up at the space of flat connections. But if you are, but sometimes you stop at the higher critical point. So this is a higher solution of the Young-Mills equations for which the curvature does not vanish. And so these are classified. It's an easy exercise. So typically they split into as a direct sum of maybe flat connection for a subgroup and the constant curvature, constant flux abelian connection. And so these fluxes contribute to the value of Young-Mills functional. So you'll know that when you stop at higher value of Young-Mills functional. And then so the associated Dirac equation, if you are stopping at the higher solution, then you have abelian gauge field with non-zero flux. And we discussed in the beginning, for the abelian gauge fields, we have an index theorem, which tells us that the flux is non-zero. You have zero modes for Dirac operator or for its conjugate. And this doesn't change when you turn on quasi-momenta. Quasi-momenta is equivalent to twisting by flat bundle. So for n equals 2, the general situation is that you just have abelian U1 gauge fields with constant flux. For n equals 2, there are mixed phases, which I will not discuss today. So now the remaining puzzle, and I have 0 minutes left, okay, is to estimate the codimension of the space of gauge fields for which your flow will stop at the high critical point. And I will spare you the details of this analysis. It's not difficult. You just need to know how many negative dimensions, or what we call relevant operators, we have at the high critical point. And with some analysis, one finds that one gets 3 relevant directions. So the codimension of the space of unstable gauge fields is 3. And we did verify that the ansatz of, for example, those gentlemen, so explicit function u, which I didn't write, if you apply Young-Mills flow, it does stop at a high critical point with flux 1, and this is why they found one zero mode. But the miracle is that how is it that with just one parameter, we tuned to arrive at a high codimension subspace? And the resolution is that there is this additional discrete symmetry. So the original ansatz and the flow, so the original ansatz had certain rotational symmetry, Z6 symmetry. The flow commutes with its symmetry. And so the space out of three-dimensional space of relevant perturbations around the critical point, you actually have only two one-dimensional, I call them mustaches, which correspond to the Z6 invariant unstable directions. And so they actually, so the codimension is actually one. And so that's why this is why those gentlemen were able, with just one parameter, tune the gauge field so it will cross the unstable locus. Now this flow is something which is can be efficiently run on a computer, and so you can use it to compute many things. So there are many future directions, and so this is some painting which I made. We made with my girlfriend some time ago. Before I got lucky with the student who actually could do the computations to confirm this picture. So thank you very much.
Thanks very much, Nikita, for giving us glimpses of quantum mechanics and mathematics interface. Senthil, maybe? Oh, okay, maybe first we'll take Bhaskaran and then Senthil.
Thank you for a nice talk. Here I am. So you talked about Heisenberg chain, spin-half Heisenberg chain, which is integrable, and the connection to gauge theories. So there is also Haldane-Shastri model,
yes,
which is integrable and very user-friendly.
Yes.
What is the gauge theory?
So Haldane-Shastri. Okay. It fits into this framework. So if that was the question, but yeah. So Haldane-Shastri is the limit. So it's a limit of the model where here you replace the elliptic function by 1 over sine squared. It's called Sutherland model. And this prefactor becomes kind of a spin-spin interaction operator. So this can be, this corresponds to a quiver theory, so the gauge theory, which has gauge groups organized around the circle.
So there is a connection.
Yes, there is a connection.
Because in some sense, Haldane-Shastri model is very simple, user-friendly, easy to understand.
Well, trigonometric models are simple. You can solve them without highbrow science. This is elliptic, and it has interesting features which might be useful for condensed matter. So this the elliptic analog of Haldane-Shastri, I'm not sure it exists. So the trick which is used in getting to Haldane-Shastri from spin Sutherland is you freeze the motion of particles. You only leave the spin degrees of freedom. This trick might not work in elliptic case, but nobody says that spins should be frozen. I mean, the real spins actually are oscillating.
Thank you.
Senthil.
I was going to ask about the last part of your talk. So I wonder whether with the insights that you have, relating it to triangles, flow, things like that, I mean, are you able to discover other flat bands?
So we were so for example, you can with this analysis you can understand what happens if you fine-tune your system so that it will have in our language flux 2, for example, not flux 1 but flux 2. So you have more zero modes. So you'll have a high-dimensional space of flat bands. So maybe you'll have some kind of a spins on top of just mobility degrees of freedom. And I don't know. So it's no, I think it's very fruitful. It's probably harder to achieve because then you do need to tune more parameters. But who knows?
First, yeah.
So just to understand the first part of your talk, are you saying that if I have a gauge theory and with some symmetries and I use this Bethe gauge correspondence, then is it possible like to create like new integrable many-body system with completely new Bethe ansatz? So
Yes. So that so what I presented was an example of that. So people didn't know the Bethe ansatz for this quantum intermediate long wave equation. It was discovered using this the relation to gauge theory.
okay, so they have used the gauge theory and then they constructed the corresponding. And the other question is, suppose very weakly break integrability. So are there any similar Bethe gauge correspondence because like very weak integrability breaking things?
Weak integrability?
Yeah,
integrability breaking. You
Yeah.
break the integrability a little
very
bit.
weakly, and then whether it is.
I don't know. It might be that it might be if you softly break supersymmetry, you can still use this. I don't know, but I will not rule it out.
Thank you.
So again, a question about the Bethe gauge correspondence. Do the spins of the integrable system mean anything in the gauge theory?
So they're determined by the masses of matter content. So maybe rephrase the
So
question.
the spins live in some Hilbert space, and, and
Right.
that Hilbert space where the spins live and so on.
So
does it
this
have a correspondence
Hilbert
in the gauge
space
theory?
parameterize this. So the states of this Hilbert space are, roughly speaking, the functions of the parameters of various defects in gauge theory. So so typically, in 4 dimensions, I can study surface defects which break the gauge group down to maybe a subgroup on the defect. And so because this breaking can occur differently on different points of defect, there is a corresponding theta angle, which measures how many times you wind around the coset space, let's say SUN over UN to the n minus 1. So the functions of those theta angles form the Hilbert space of the spins.
Yeah, I had a small follow-up. I think it's sort of in a related vein. So there appears to be no obvious connection of this integrable spin chains to the ones that people study in the planar limit for the anomalous dimensions of the. But is there some way to maybe connect them?
Yeah. So when people, the way I think about it is that if you take n equals 4 super-Young Mills, planar n equals 4 super-Young Mills, and compactify it on a 3-dimensional sphere, so you get quantum mechanics of sorts. And so that's the quantum mechanics which is the spin chain that people are studying. So it surely has Bethe gauge dual. In fact, it has for different sectors. So for different charge sectors, it has different Bethe gauge duals, but we haven't yet identified it. It might be that you need the totality of n equals 2 theories and 2 dimensions to describe all of it. But the reason why it hasn't been identified is that I think these are theories with less supersymmetry. They have 0, 2 supersymmetry as opposed to 2, 2. So for experts, the problem is the dressing phase. So in all textbooks on spin chains, Bethe equations have what's called Young-Young potential. So these equations, even though they describe quantum states of something, they actually have yet another classical interpretation. So there is some kind of Hamilton-Jacobi potential such that the derivative of that potential with respect to its arguments is an integer, is equivalent to Bethe equation. This breaks down for n equals 4 super-Young Mills. Now, the reason why it breaks down has to do with the central extension of Youngian algebra for very special super algebra, but the work of Maldacena and Hoffman, I think. Was it right? I take credit. You take credit, okay. So it suggests that there might be a way to see this dressing phase as a limit of something which has a potential. And so the fact that they have some gamma functions which are hallmarks of things which are derived from 4-dimensional gauge theory suggests that it should fall into this category as well. Maybe with my soft breaking to 0, 2.
Just a little comment that might help to demystify this notion of Lifshitz thimbles. supporting your view, I often speak about this as real physics in the complex plane. Now, it occurs in the context of the oscillatory integrals that represent interesting objects in physics. And typically, you expand about a stationary point, a critical point. Now, these expansions almost always diverge because there are other critical points which give you exponentially small instant-on contributions. Now, not all of those other saddle points are accessible from the one that you are going through. And the Lifshitz symbols gives you a criterion for determining which of those other saddle points contribute and give you exponentially small contributions. Now, you can go a lot further using repeated resurgence and get exponentially better approximations improved at each stage. And at each stage, it's this construction which tells you which of the more and more saddles are accessible and therefore contribute. So you get this cascade of ever-improving small exponentials which involve more and more saddle points determined by this construction. Just a little comment.
So I think
we call it hyperasymptotics. Okay.
Right. So I think what's there is an honest thing which one should be doing, which is very hard. The honest thing is to study for each Lefschetz. So the way I defined Lefschetz symbols were just all possible contours of integration of an analytically continued expression. But the original problem had a specific contour, which was space of real fields. So the space of real fields as a cycle in space of fields decomposes with, let's say, integer coefficients in those Lefschetz symbols. Some of them contribute 0, some of them contribute with some signs. And for each symbol, we need to solve the hard problem, which is to find whether there is a solution of this gradient flow equation, which I didn't write for that problem, which starts at a critical point, which is complex, and ends up on a real slice. Now, my suspicion is that the methods of resurgence approach this problem in a maybe kind of with some approximation scheme. But I don't know whether this is the universal approach or it works in some cases. So, but there is some convergence of ideas there, that's for sure.
Thank you.
Yeah, Poonam.
Yeah. So my question is, there is a...
I think it's not on, maybe.
So my question pertains to something called non-Hermitian quantum mechanics.
Okay.
There's a whole lot of literature starting from Carl Bender's work where it was shown that if you have PT symmetric scenarios, then you can get real eigenspectra. So how would you, are people worrying about looking at?
So in my story, I don't care that much about the real eigenvalues. I study, so typically the Hamiltonians which I have, there is some real locus in the space of parameters for which these Hamiltonians are Hermitian, so can be realized in the Hilbert space. But then I don't have to stay within this real locus. I can do the analytic continuation in the complex domain, which is natural in the context of gauge theory, because in gauge theory, in unitary gauge theory, these operators have truly complex parameters. And so I'm pretty confident that the eigenvalues which you will find on the Hermitian slice will continue nicely to some complex analytic functions of parameters in the complex domain. They have very interesting monodromy, so Berry phrase at work, and the wave functions have very interesting monodromy. But I don't require PT symmetry, so I don't require. So there is something like PT symmetry which has to do with the fact that the Planck constant in these systems has geometric origin, and it had to do with the rotation of space or some part of space. So you can rotate in the other direction. So there is some kind of a symmetry which flips the direction of rotation, which changes the sign of a Planck constant, and that changes. So it is interesting symmetry, but it's,
thank you.
Okay, thank you. So let's thank Nikita again for a very stimulating talk.